We're continuing our discussion of the quantum mechanical harmonic oscillator. In part A, we've determined that this commutator, A minus A plus commutator, is equal to 1. And then we have computed A plus A minus applied to psi. And then in part C, we have written the Hamiltonian operator in terms of A plus and A minus operators. Let's move on to part D. Determine the commutators Hamiltonian A plus or A minus. So let's, because we have done this exercise in part C, this will be rather simple. So square brackets, Hamiltonian operator, A plus operator, Hamiltonian A plus commutator. Let's see what this is. So first, we have to apply the A plus operator and then the Hamiltonian operator. So we have the Hamiltonian operator is H bar omega. It is written in terms of A plus and A minus operators in part C. A plus A minus plus 1 over 2. This operator which is our Hamiltonian operator, comma A plus is our commutator we're after. And that's equal to, you can see the first term will be H bar omega, A plus A minus A plus operator, plus H bar omega over 2, A plus operator. And then we switch the order of the operators. So A plus goes to the first term, and this is the actual operator we apply first. So that's going to be a minus H bar omega, A plus A minus. So minus H bar omega, A plus A minus. And then we have H bar omega over 2, but with the minus A plus operator applied afterwards. So this is minus A plus H bar omega let's move this a little bit to the left. A plus H bar omega divided by 2. Okay. Now you can see that I have H bar omega A plus and A plus H bar omega over 2. So the order here doesn't matter. So these two are the same. They will cancel out. And here I have H bar omega A plus A minus A plus. And here I have minus H bar omega A plus A minus. So what is this? So this can be written in H bar omega parentheses. This is equal to H bar omega A plus operator applied to A minus A plus minus A plus A minus. And that is H bar omega A plus operator applied to A minus A plus commutator. And we know that commutator is equal to 1 from part A. So that was our result in part A. So we can substitute that here. So we get the Hamiltonian operator A plus commutator is equal to H bar omega A plus. And the other part of the problem is asking us similarly for Hamiltonian operator a minus operator commutator. So we're going to calculate this commutator, H a minus, and remember, so this is going to be very similar to what we have here. The only thing is I'm replacing a plus with a minus in my end result. So this is going to become h bar omega a minus. Okay, so that's the only thing that changes here. So this sign changes from plus to minus. Let's move on to part E of the problem. Consider a wave function psi sub n with definite energy E sub n, whereby Hamiltonian applied to psi is energy times psi. If we define a new function psi n plus 1, which is a plus applied to psi sub n, then we can readily determine its energy by computing Hamiltonian applied to psi sub n plus 1, which is Hamiltonian applied to a plus psi sub n, which is a plus Hamiltonian plus Hamiltonian a plus commutator applied to psi sub n, and comparing the result with En plus 1 psi n plus 1. Finish this calculation by inserting what we have determined to find the energy of the n plus 1 state in terms of E sub n and n. Okay, so I'm going to go with the suggested calculation. Hamiltonian operator applied to the wave function psi sub n is equal to energy of the nth level psi sub n, and psi sub n plus 1 is equal to a plus operator applied to psi sub n. Now this operator is increasing, and so you can see that we can call this the raising operator actually. So Hamiltonian operator applied to psi n plus 1 is equal to E n plus 1 psi n plus 1. So we know this result. Now Hamiltonian operator commutator with a plus applied to psi sub n gives us Hamiltonian operator applied to a plus psi sub n minus a plus operator applied to Hamiltonian psi sub n. A plus applied to psi sub n gives us psi sub n plus 1. So Hamiltonian operator applied to psi n plus 1 minus a plus operator applied to Hamiltonian times Hamiltonian operator applied to psi sub n, which is En psi sub n. And this is equal to you can see here Hamiltonian applied to psi n plus 1 is En plus 1 psi n plus 1, and then I have En multiplied with, because these can change order, it's just a product, this is a number, a plus applied to psi sub n gives me psi sub n plus 1. So this gives me the energy difference En plus 1 minus En applied to psi sub n plus 1. Okay, now Hamiltonian operator applied to a plus, Hamiltonian operator with a plus gives us, this commutator gives us h bar omega a plus. So this is actually equal to h bar, this thing is equal to also h bar omega a plus applied to psi sub n, which is equal to h bar omega psi n plus 1. Because we have shown that this commutator is equal to h bar omega a plus. So if I apply it to psi sub n here, that's what I'm doing. So these two are the same. So psi n plus 1s will cancel out, And I will find that the energy difference between the m plus 1 state and the nth state is equal to h bar omega. Let's move on to part F. We can prove that the lowest energy wave function psi0 is annihilated by A minus, meaning that A minus applied to psi0 is 0. Using your expression for the Hamiltonian in terms of A plus minus, determine the ground state energy E0. Hamiltonian operator applied to psi0 gives us E0 times psi0, Schrödinger's equation. Hamiltonian operator written in terms of A plus and A minus is A plus 1 over 2 h bar omega applied to psi0 is equal to E0 psi0. So the first term here is A plus A minus psi0 applied to psi0 h bar omega, and then we have plus h bar omega over 2 times psi0 is equal to E0 psi0. If A minus applied to psi0 is 0, as suggested, if this is 0, then I will have E0 is equal to h bar omega over 2. That's the ground state energy of the quantum mechanical harmonic oscillator. Now let's move on to part G. By applying A plus repeatedly, we can generate all higher states. The energy of the nth excited state can be determined by considering Hamiltonian operator A plus applied n times to psi0 is equal to E0 times psi0. Using the above results, determine E sub n. Okay, so from part E, I have E1 minus E0, because for two consecutive levels, the energy difference is h bar omega, is equal to h bar omega. So E1 is equal to h bar omega plus h bar omega over 2, which is E0. And similarly, I can write E2 minus E1 is h bar omega. E2 is 2h bar omega plus h bar omega over 2, etc. So for the nth level here, En, I will have n plus 1/2 h bar omega. These are the quantum mechanical harmonic oscillator energy levels. Okay, so what have we done here? So Hamiltonian operator applied to psi0 gives us a E0 times psi0. If we apply the A plus operator nth times on psi0, we will be generating higher energy levels because it will increase the state number. So for the nth excited state, we can use the above results to determine E sub n, because En plus 1 minus En we have found to be h bar omega, and the ground state energy, knowing that A minus applied to psi0 is 0, is h bar omega over 2, we can find the energy levels as n plus 1/2 h bar omega.